There's a second way to calculate your localization. So this is called as localization using observation model. Let's take the only 1D case as an example. So there's a wall like this. I'm traveling here. That's my robot, and there's a sensor which is ultrasonic that is right at the center, and it goes here, it comes back. So I know this distance, I know the distance of the robot. So my position, keeping this thing as the origin and keeping this thing as the positive x. So my position is always the ultrasonic reading, which is true reading plus noise. And this is constant. That means even after 5 hours, I'll have just a constant error. It's not that the errors are increasing with time. The errors are constant. They may be large, depending upon the resolution of the ultrasonic, but then my positions are what are constant with time. And therefore, let me give you two examples. So there are two common sensors that we use. The first one is called as a LiDAR, which is just a laser beam which travels all the way, and the laser beam goes, comes back, goes, comes back, goes, comes back, and as it goes all the way, we measure the distance of it. So that's the first kind of way by which you can actually measure the sensor. And the laser beam is nothing but a normal laser pointer by which we measure distances. So this one has a laser pointer, it goes, it comes back, and it gives me the distance over the panel. The only thing is that this one will rotate as it goes along. So that's the first sensor. And therefore, let me take the same kind of a map that I have simplified for reasons. So let's say this is the environment that I have. And let's suppose that because the map is already known, the position of all these coordinates is accurately known. So all corners I know the position. Say this is what my robot is. It invokes this laser readings. So I get in some kind of a laser map, and using techniques which are very similar to your image recognition. How do you find corner in image recognition? I find out what these corners are. So I say I know position of all corners in the world I know all corners seen by me in the LiDAR image and I need to calculate my position. So, and firstly, what's a LiDAR image? So, let's say the robot was looking at here. that's the laser beam that's at a signal of alpha, and this reports the alpha. So I can say that there's an obstacle at a distance of the alpha, cos alpha and sine alpha relative to the robot. And using all these obstacles, I will take all these points, I'll take an empty canvas and I'll put all the dots in these points. So for this one, that's exactly how the LiDAR image is gonna look like. If I plot all these points in an empty canvas, I'm gonna get all these points. That's exactly how a LiDAR image will look like. And using this image, you can see that I can easily find out the corners. It cannot see this obstacle. Okay, it can see some parts of this obstacle. So let's take any one corner, which is O. Now, if you have a brief background of transformation, so you would be able to guess that I know the position of the corner in the real world. So let's say this is the position of the corner in the real world. And I know this xy, which is the position of the corner in my own coordinate frame of reference. So this is the position of corner in real world, and this is the position of corner in my local coordinate frame. So if at any general point, if this is a robot, this is what the coordinate frame is. And of course, I do know this is the corner in my local coordinate frame. I multiply with a transformation from world to coordinate, my local coordinate frame, which is nothing but the pose of the robot. And this should be equal to O in W. I know this, so I can calculate this. The only thing is that I have too many corners, so I'll optimize it like, I'll solve it like an optimization problem. For all corners O. And what's important is you really need not take corners. You can do it for all the points in the LiDAR image. So let me take that as an example as well. And that's what is my localization problem. So this is arg min of this objective function. Okay, so far so good. So I'm assuming that the correspondence problem has been solved. So basically I have 1, 2, 3, 4, 5, 6, 7 corners that I see over here. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16 corners here. So I actually need to select which corner am I probably looking at. You could do it, of course, by using signatures, using internal angles, which will not be very helpful over here because they're all close to 90. You could do it basically, you know, the approximate position, and then you say find out that, okay, if I know the approximate position, then the close by to that position is this corner. So I'm probably looking at this corner. Now, sometimes what you can also do is, in order to calculate the position, you have first LiDAR image like this, taken by the robot at time t. So, and you also have this map. So you basically take this image and try to overlay it in the entire map and see where does it match. So overlay this image on map. And of course, in the map, you'll only look at, I mean, the robot cannot look at inside obstacles. So, I mean, all the obstacles will just become the boundary. And position is the best overlay. So, position is the transformation with the best overlay. So that's how you find out the position using a LiDAR as a sensor intuitively. I'm not going into details because the course on humanoid robotics is supposed to take it with a mathematical detail. And I can do exactly the same thing using a vision camera as well. So this is the same camera by which I am recording this lecture. So it's a webcam. And the robot looks at some boxes, it looks at some lights, it looks at some doors. I know the corners of all of these. And I know these corners in the real world, and therefore I first identify which object am I looking at, which corner am I looking at. I calculate its two positions. So let's say it is exactly the same thing, O, and now let me call this as L, which is a landmark. And let me draw one landmark over here. So I know the landmark in the world. What I also know the landmark is in my camera coordinate frame. Suppose I have a camera which is right here, and suppose there is a stereo camera if you want to calculate in the depth. Let me do it for the monocular camera case to make it more interesting. So I convert this into the robot coordinate frames, assuming that my position is Q. This is unknown. This is what I need to find out. But then this is what gives me my position of this landmark in my own coordinate frame. It passes through a projection matrix, which is called as a camera calibration matrix. So this is the function that basically projects a 3D point in the camera's coordinate frames into the point in the image. So it's called as a projection function. I know a point in the 3D world, and I also know that this is my camera lens. So this camera will inverted principle point camera. So this ray will come over here, and this is where the inverted image will get formed behind the focal length, or this is where the forward image will get formed ahead of the camera at a distance of the focal length. And these are functions that of course you have studied in image processing classes. So this gives me what is my u and v coordinate axis. I also have u observed and v observed, and I need to minimize this error. So augment. Actually the position, I'm not going into the detail, is the transformation from world to the robot and not the other way around. While we're using the other way around matrix, so we of course know TQW is TWQ inverse. I'm not going into the mathematical detail, I'm just telling you what the intuition is. So the intuition is simple, that I have a object and I know all its corners, and I also have a camera. So I find out where the projection of this object in this camera's image is if my position is Q, and I find out what is the best position possible such that I see this camera in my image at exactly the same point where I actually saw it in the actual image. So let's summarize this over here. I calculate best pose such that L as it should be observed if robot was at Q. So calculate the best pose such that the landmark as it should have been observed if the robot was at Q is as close as possible to where L was observed in the image taken by the robot. This is submitted over all landmarks. So intuitively that's clear. That's the second way I can calculate my position. I say that for a number of entities, I know their corner's position. I know that there's a function. If the robot is at this position, it'll observe it here. If the robot is at this position, it'll observe it here. If the robot was at this position, it'll observe it here. I find out the best position such that in that position where the robot is expected to observe, the landmark is exactly where the robot observed it. That's up. So intuitively what it says is that I have a camera and I have an object and I know where is this object in my camera's coordinate frame. I know where this object is in the world coordinate frame, so I can calculate where this camera is in the world coordinate frame, and that's a problem of localization. Simple enough.